So we're going to do the third type of line integral today, which is known as differential form. And the good news is this type 3 line integral is really a type 2 line integral that somebody already did the dot product for you. So let's just do a quick recap of last time. Last time we looked at a new kind of line integral, and it involved the dot product of a vector field f with the velocity vector, or the derivative of a vector valued curve. And this is what I call the type 2 line integral. Okay, and this is not something you'll see in the book. Because there's 3 types of line integrals, I've just denoted this one the second type. So hopefully you reviewed that and you're doing some homework on that, and it hopefully makes sense. So let's take a look at the third type. So if you have a vector field f, and we're looking at a 2-dimensional vector field, so the components denoted m and n, and m and n are themselves functions of x and y. So let's say somebody already parameterized your curve for you. So you've got a nice vector valued function, x of t, y of t. And of course, with that, you also, I just want to mention, anytime you're doing a line integral, you better have, or you need to give, if you're parameterizing, the range of time, the time interval that the curve you're integrating over. So f dotted with dr, I'm going to do this in slow motion so you can see what's going on. You've got your m and your n, and you're going to dot product that with, x prime of t, y prime of t, like this. So when you do this, you're going to get m x prime of t plus n y prime of t. But what we're, and I should say there's a dt here also. So then if I do a little bit, I'm just going to switch notation. X prime is the same as dx dt, and y prime of t you could rewrite as dy dt. See of this? Okay, and then if you distribute this dt and then pretend these differential form written derivatives are fractions where you can cancel, the dt's cancel, and then what you get is m dx plus n dy. And that's the final thing. So then this line integral here, this f dot dr line integral, after somebody did the dot product for you, it's going to look like m dx plus n dy. And so if you're given a line integral with that kind of flavor, it's called differential form. So this form for a line integral is called differential form right here. Okay, so we're going to finish out 17.2 line integrals with a whole bunch of examples with differential form. And in the process, we're going to be doing like parameterization, because I don't believe I've done enough examples of that, because you are going to need to do that. Put a line integral on a quiz, nobody bats an eye. Make the line integral equal to 0 and everyone loses their minds. And a line integral can equal 0 if it's a type 2 or type 3. That's possible. Remember that line integrals can represent work done. Remember we talked about this? The application is work done on an object as it's moving around in some force field. Yeah? Questions? So let's do a differential form line integral. So how do I know it's differential form? Because it looks like it. Look at this. You've got something times dx plus something else times dy. And it's, so this xy that's multiplying with the dx, that's your m, and the x squared is the n. It's understood. It's understood. So your vector field, if they asked you, well, what's the vector field that goes with this line integral? By cherry picking off the factor that's multiplying with the dx and the factor that's multiplying with the dy, you can reconstruct the vector field that's in this situation. So it's not a mystery. So the vector field's involved. So this is a line integral involving a vector field. So the hard part about this letter A example that I put in here into your lecture notes is they're giving you the curve and they're describing it for you, but they're not parameterizing it for you. You got to do that. They're not being nice and they didn't give you the R of t. So they're giving you the starting and stopping point. So I'm going to sketch this even though they didn't ask for a sketch. It just kind of helps. So if you graph the function y equals x squared, I think everybody knows that's a parabola. And the part of the curve we're interested in is we're starting here at the point 0, 0. And then remember, orientation matters when you're doing line integrals, and we're stopping at the point 2, 4. So let's say this right here is the point 2, 4. So we're only integrating over the portion of the parabola between 0, 0 and 2, 4. So how do we parameterize that? You got to do it. So what do you do to parameterize? I need you to show me two things when you're taking a quiz or exam if you want full credit. You have to give me the R of t equals, and that's your vector value function, and you have to tell me the interval of time that's that vector value function is doing his thing for the curve that they described. So this is not too hard of a problem. I told you how to parameterize like 2 or 3 months ago when you have a function of x. So when you have a function of x, y equals x squared, that's a function of x, you let x equal t, and then y, since y is equal to x squared, it'll be equal to t squared. And now, sometimes this is the hard part, what starting and stopping time will match the start and stopping points? Well, I hope you can see, since we did let x be t and x is starting and stopping x coordinates at 0 and 2, we can easily let our time start and stop at 2. It's not always going to be that easy, but this one it is. So beautiful, we have our vector value function. We did the parameterization. Yay! And I will give you partial credit for that. Not a lot. Like if it's a 10-point problem, okay, I'll give you a couple points for parameterizing if everything else is wrong. Now what? Well, you do need to still get your R prime. That is always going to be one of the things you need to do on all 3 types of line integrals. It's required. You got to get your R prime. But the good news is you don't have to get speed. You know how on the scalar line integrals, you had to go find the magnitude of R prime? You do not need to do that for a type 2 or type 3, because remember it canceled? I did the derivation for you last time. That magnitude canceled. So you don't need to find that. Yay! One less thing to do. But you do need to rewrite this line integral as a regular integral that you can actually integrate. So how do you convert it to something we can actually integrate? Well, it's going to be a single integral. The starting and stopping times we got 0 seconds to 2 seconds. And then you're going to start substituting. So you're going to have to rewrite xy dx plus x squared dy with t's. So you're going to do a similar kind of substitution. So in place of any x that shows up, you're going to substitute the x component from your vector valued function. So you'll have t times y, but y is t squared. Now the dx is going to be the x component from your r prime. So you're going to go 1. It's really 1 dt, and I'll put that there. But you'll see the dt kind of factors out, and I'll pull it out. And then x squared, so for us that'll be t squared. dy is really this 2t dt. And this is what you're going to integrate with respect to t. So what I usually do is I like to factor out my dt, since it's common to both. And then I'm looking here, this is t cubed, and then this is 2t cubed. Okay, those are like terms. How about if we combine them? T cubed plus 2t cubed is 3t cubed. Oh, this is super easy to integrate. Nice. So let's see, my antiderivative will be 3/4 t to the 4th, and I'm going to evaluate between the points 0 and 2. And so I'm going to end up with, what the heck, 3 times 16 over 4. And I think that reduces to 12. And I'm done. So there is your first differential form line integral. Congratulations. So let's keep going. Here's another one. What's the difference between this one and the other one? Well, the good news for this one is they were really nice to us. They gave us the parameterization. So when you're given the parameterization, say thank you. It's like, oh, good. That was very nice of them to give us the parameterization. We don't have to do it. Whew, one less thing to do. So it's an easier problem. So you're still going to need the R prime. You still need that, 2 and 10. Oh, that's nice. It's just a constant. And you're still going to do some substituting to convert this differential form line integral into a regular integral we can do business with. So 0 to 1, they gave us the time going from 0 to 1 seconds. So you're going to have y minus 3x dx plus x squared dy. So you're going to do like this, but you're going to substitute because I need only t's to show up. So the y gets replaced with the y component from the vector valued function minus 3 times the x gets replaced with 2t, the x component. Now the dx gets replaced with the r prime's x component, 2 dt, plus x squared. So for us, that'll be 2t squared times dy will be 10 dt. So this is what we have to integrate. And so I usually like to clean it up by factoring out my dt. And what the heck is this? This is 10t minus 6t, but that's 4t, but 4t times 2 is 8t plus, and then when I do 2t squared, that's really 4t squared, but then multiply it by 10, I get 40t squared. Okay, this isn't too hard to integrate. It's just a polynomial. Antiderivative is 8 times t squared over 2 plus 40 t cubed over 3. Evaluate between 0 and 1, and I end up with 52/3 after I do some arithmetic. Okay, and there's another differential form line integral. Let's do another one where I'm going to give you a little slickadoo trick you can do, but only in certain cases. And then also there's a little extra thrown in here that I'm going to allow. And some professors don't allow it. So I just want to say, be careful, because if you tutor somebody in this class, or a friend or whatever, and you tell them, hey, I do it this way because Professor Rasky said it's okay, and their teacher might mark them wrong because their teacher may not allow what I'm going to allow you to do. So you'll just say thank you that I'm going to let you do this. Listen up. Here we go. So say you're given a curve in 2D, so it's going to be a 2D line integral, and you're given x goes from a to b. You can parameterize the curve by just letting x be t, I told you that, for functions of x, and y be f of t. And it turns out you can evaluate the line integral in either the variable x or t, although traditionally, as you saw, I like all line integrals to be in terms of t. But for these super easy ones, you can stay in the world of x if you're careful. So here, suppose y is equal to 4x minus x squared. Okay, then dy is 4 minus 2x. Okay, dx. And then dx is just itself, dx. Okay, so what? So this differential form line integral is going to become the integral going from, and they're giving you a starting and stopping point, x going from 4 to 1. And this is the part where some teachers won't let you do it. Here, since x begins at 4 and the ending point has the x coordinate as 1, you notice how this is weird limits of integration where your lower limit is a number larger than your upper limit. Some professors won't allow you to do that. I'm going to let you do it if you're doing a type 2 or type 3 line integral. Type 1s, no. Remember I told you type 1, you have to be careful. Your time has to be moving forward. You're essentially letting your time move backwards here. You're essentially saying, hey, I'm going to let x be going from 4 to 1, even though this looks like impossible or backwards. You can do this if you're doing a vector line integral. It'll work out okay. Now, if you don't want to do it that way, we can discuss another way to do it here in a moment. But here's the deal. Y dx, you replace y with 4x minus x squared. Dx is just himself. Plus, x stays himself, x squared. And then the dy was 4 minus 2x dx. And then you want to distribute your x squared here, so you'll get 4x squared minus 2x cubed. And you can factor out the dx here. And what do you have? 4x minus x squared plus 4x squared minus 2x cubed, going from 4 to 1. And I like to combine my like terms just because it's a little bit more streamlined, so I can combine those two middle terms, the x squared terms. And when I anti-differentiate, I get 2x plus x cubed minus x to the 4th over 2. And you're going to go from 4 to 1. I know that seems weird, but 2 times 4 minus 4 cubed minus 4 to the 4th over 2. Or excuse me, I'm doing it back. I just said don't do it that way. Okay, sorry. I'm trying to do this too fast. I plug in the upper limit, which is 1. And then minus the lower limit, which is larger. And we'll get the right answer. And after all is said and done, I get 69 halves. Okay. Now, if you were in, if you're looking, my math lab doesn't let you do this. Okay, where you have your decreasing limits of integration. So you have to be careful, because if you're doing one of those setup problems on my lab math, it'll probably mark you wrong, even though it might be right. So what is another way to do this problem that would be more traditional, or more in alignment with the orthodoxy? The orthodoxy would say, okay, when you're parameterizing your vector valued function, instead of t 4t minus t squared, where they're not going to let you do that, because you're going to have your time moving backwards. So they don't like that. So a better way would be, say, 4 minus t to be your x. And then everywhere you see an x in your y function, which is 4x minus x squared. And then you let time go from 0 to, what's going to work out here? I think 3. Let's see. Oops. See if that's going to work. See, if I plug in t equals 0 here, I do get an x starting at 4, which is good. And when I plug t equals 0 here, what do I get? I get 16 minus 16, which is 0. Perfect. I get the starting point. And then if I plug in my ending point, keep in mind I want x to stop at 1. If I let t end at 3 seconds, then I will get a 1 here for the x coordinate. And then if you plug in a 3 for the y, what do I get here? 4 times 1 minus, is that going to work? 4 times, oops, 4 times, yeah, 1. And then when you plug in a 3 here, minus 1 squared, so that will give me a 3. So that looks like it will work. So this is a different parameterization. And so what happens? Well, then this line integral y dx plus x squared dy becomes this line integral, where time goes forward. You're going to do everything in terms of t's now. So I'm going to get my r prime, and then I'm going to have what? I'll have a -1 here. What is my, this is going to be -4 minus 2, 4 minus t times -1. You're going to have, it's going to be a little bit messier to do the substitution. So y is going to be, oh dear Lord, what did I get myself into? This mess times dx, but dx is the x component from your vector valued function's derivative, and then plus x squared, but we said x was 4 minus t, so 4 minus t quantity squared, and then dy is that, you can, I'm going to multiply -1 times -2 to get a +2, and you can multiply all this out. and then dt. And I claim this answer, I'm not going to do the rest of this, it's just going to be a pain. No matter what your parameterization, as long as it's honoring everything and honoring the orientation as well, you should get 69 halves. Okay. Let's do one more. Let's do a 3D differential form. Okay. I do want to say that the textbook we use, Briggs, is not that strong. I'm being charitable. It's awful for Calc 3. And it has very few differential form problems in it. So good news, you got me as your instructor. And other books are very much more strong, and they're into differential form more, and it's a very important format. And so some of your MyLab Math homework I actually pulled from other books that are available in MyLab Math. And so I have you doing this format because it's important. So let's look at a 3D differential form. So if you have a 3D vector field with components M, N, and P, and I think Briggs uses P, Q, and R, whatever. And those components are themselves functions. This time they're functions of X, Y, and Z because we're working in 3 dimensions. And your curve, vector valued function, X of t, Y of t, Z of t, and you also need some time. Time has to be going on some interval. Then F dotted with dr, and I'm just doing this derivation again, is F dotted with dr dt, dt. And so this is somebody doing the dot product for us already. And what's it going to look like when all is said and done? It's going to have this format. It's going to look like the 2D, but we're extending it to have one more term. One more term, P dz. So here's an example of a line integral in differential form with a 3D vector field. Okay, so it's understood that this junk that's multiplying with the dx is the m. It's understood that the junk that's multiplying with the dy is the n from our vector field. And it's understood that the junk multiplying with the dz is the p component from the vector field. That's all understood. You have to know that. Otherwise, when we get to the end of today's lovely, dazzling lecture, you will not be having fun when somebody says, yeah, go use the fundamental theorem of line integrals. You go, what? Okay, they're giving us a starting and stopping point, but they're not telling us what t starts and stops at. That's our job. Because they didn't give us the curve, they just told us about the curve. It's a straight line starting at this point. So this is the starting point and the stopping point. You have to parameterize. Well, they didn't tell me to. Yeah, but that's part of the problem. You have to understand when you're given a line integral problem, a word problem or whatever, and they don't give you R of t, and they just tell you some conditions that have to be met for the curve, or they're giving you what the curve, criteria is. You have to come up with the R of t. Sorry, you have to do the work. Go figure it all out. All of these question marks, you have to fill in those blanks, even though they didn't explicitly say so. So you need to get that. So good news though. You guys have parameterized lines since the last 2 months. So if somebody gives you a starting and stopping point, remember you get the PQ direction vector. Yeah. And then you get your X of t, essentially your Y of t, your Z of t, your parametric equations. You've done this before. And we'll just use the 0, 0, 0 as our point, and 1 times t, 3 times t, 2 times t, put it all into a vector valued function, sure, over here. And then what are your starting and stopping for your time that's going to match the starting and stopping points on this line segment? Well, if we let time equal 0 seconds to start, that'll get us at the point 0, 0, 0. And if we let time equal what? What do you think? That will get us to the stopping point 1, 3, 2.
1.
Yeah, 1. You plug that in your vector valued function here, t, 3t, 2t, you'll get the point with coordinates 1, 3t. So here we have the parameterization. Yay! That's worth a point or two on a problem. You are going to need your r prime, and r prime is going to be a constant, as it always is when you've got a line. And then you start doing all your substitutions. You have to rewrite the differential form into an integral you can do business with. So it's going to have the limits of the time constraint there, 0 to 1, 2 x, y, z, dx. You'll rewrite that as 2. T, that's what you substitute for your x. 3t is what you substitute for y. Z gets replaced with 2t. Dx is just 1. This right here is your dx, dy, dz here. 1 dt plus second term, x squared z dy. X gets replaced with t, so you got to square it. Z, you substitute a 2t, and dy is 3 dt. Plus, and then the last term, x squared times y, that's replaced with a 3t, and dz is 2 dt. So this mess is what you're going to integrate. And notice that all these terms have a dt, so just factor that out. And then look at these powers of t here. Oh my, 2 times 3 times 2, I believe that's 12. And then you have t multiplying 3 times, 3 factors. Here, oh boy, what is that? 6t cubed. And then here, I think I have another 6t cubed. All right, well, these are like terms. How about we just combine all those together before integrating? I mean, you don't have to, but it sure makes it a little bit more efficient here. And this isn't too hard to integrate. And you can reduce. And I just get 6. Okay. And there we have a differential form line integral in 3D. And we're officially done with this section. So what's the recap on this section? The recap is it's a pretty juicy section. So you're going to need to take some time to look it over, read it over, review, do some homework. And it's basically going over line integrals, all 3 types. So let's look at the next section, conservative vector fields and independence of path. Well, what does this have to do with line integrals? Oh, it's got everything to do with line integrals. Don't worry. That's not going away. We're still here doing line integrals, like for real. Really? Yeah. In fact, this page right here is quite the doozy. I'm going to kind of go through it quickly, but it's going to make a point, and then the next page we're going to do a whole bunch more line integrals, boom, 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 and we'll make a different point. And so the question is, what's the point I'm trying to make with this page versus the next page? So you're going to see that the 2 vector fields that we're working in have some differences, and that's going to be the key on why what happens is going to be happening. So here they didn't give you a vector field. Well, yeah, I know, but remember, you can recover the vector field if somebody asks you what the vector field is that goes with this line integral. The junk that's multiplying with the dx, that's your m, and the junk that's multiplying with the dy, that's your n. So here's your m, here's your n. Okay. And you don't have to do that, but I just want to point that out because it's going to be very key that you get that in order to complete this section. Okay, so we're going to use that same line integral that they gave here 3 times for 3 different curves. Oh man. So the first curve is, and we'll graph it, it starts at the point 2, 1 and ends at the point 4, 1. That's the first leg of the journey. Then it goes from 4, 1 to 4, 5. Okay, so I claim there's 2 legs of the journey, C1 and then C2. So for letter A, your curve is the union of C1 and C2. What does that mean? You're not going to like this, but in order to do letter A, we're going to have to do 2 separate line integrals and sum the results. Oh yeah. So let's do C1 first. So if you parameterize this leg of the journey, where you start here at the point 2, 1 and end at the point 4, 1, and parameterizing, I'll call it R1 of t. Remember, you need to give me the vector valued function as well as the time constraints. So notice that the y coordinate, and this is a straight line, so you can just parameterize using, get the direction vector and so on, but I'll do it sort of like bootstrap it in there. The y coordinate stays constant the whole time. And x is the one that's varying. It's varying between 2 and 4. Okay, so I'm going to have my time begin and end at 2 seconds and 4 seconds respectively. And then R1 prime is just this constant vector 1, 0. So the line integral C1 for this becomes the the regular integral going from 2 to 4, and then we're going to do the replacements. xy dx becomes t times 1, and then dx right here is 1 dt, plus, and then x squared dy, that's t squared, and then dy is 0. Is that right? Yeah, that's zeroed out, so don't bother. You only have to integrate t with respect to t. So that's t squared over 2 going between 2 and 4. So what's 4 squared over 2 minus 2 squared over 2? Well, I get 6, but you're not done because you need to do the other leg of the journey, the C2 portion. Oh, man. Yeah. So you're going to parameterize this vertical line segment here, beginning at 4, 1 and ending at 4, 5. Since x stays constant the whole time at a 4, let's just make him a 4. Y is the one that's variable, so let's just let the variable be t. And since y is beginning at a 1 and ending at a 5, how about we'll have t go between 1 second and 5 seconds. That works. That matches the line segment. And you always need to get your derivative of your vector value function anytime you're doing a line integral to get your dx and your dy. So then this line integral over the curve C2, xy dx plus x squared dy, becomes the line integral with limits 1 and 5, and you'll replace x with 4, you'll replace y with t, dx is 0, haha, nice, plus x squared, that's 4 squared, dy is 1 dt. So you're really only integrating 16, but that's going to be 16t between the limits of 1 and 5, and I get 64. So my final answer for letter A is going to be the sum of 6 and 64, which is 70. And I'm done with letter A. Ah, whoa. You had to do both line integrals because this curve is a piecewise curve. It's got a corner in it. Woo! Okay, letter B. Next up, letter B. So you're going to do the same line integral, but you have a different curve. So it's going to be a straight shot from 2, 1 to 2, 4, 5. So there's your curve for letter B right there. It's a straight shot. So you can parameterize it, the curve, in a few ways. You could use your knowledge of algebra and get your y equals mx plus b. And then since that's a function of x, let x be t and y is mx plus b. So that's easy. That's an easy peasy way to get the parameterization, or you can use your parametric equations knowledge and get the direction vector and all that. There's always more than one way to skin a cat when you're parameterizing. So let's just do the algebra. Let's go back to algebra class. Why not? You know, what's the slope of that line segment? Well, you guys know it's going to be the change of y over change of x. Come on, you've done this before. You know, take the difference of the y coordinates and divide it by the difference of the x coordinates. Okay, 5 minus 1 over 4 minus 2. I get 4 over 2, which is 2. There's the slope. And then you use your point slope form for the equation of a line. That's a nice, fun algebra thing. And you got your slope. It's 2. And you can pick whichever point you want to do business with. You can use the starting point here, 2, 1, or the 4, 5, your choice. I'm just going to use the point 2, 1. So you'll have x minus the x coordinate, which is 2, and then y minus the y coordinate, which is 1. And this is the equation for the line. I'm just going to clean it up a little bit, distribute, add 1 to both sides of the equation. And I get y is equal to 2x minus 3. And if I'm going to parameterize that, then my r of t, since that's a function of x, I'll let x be t, and y is 2x minus 3, so that's 2t minus 3. And now I have to choose an interval of time that matches the starting and stopping points of this line segment. So what should I do here to make sure that I start here at 2, 1, but finish at 4, 5? What should be my starting and stopping times? What do you guys think? Thoughts? Okay, okay, so we have the starting and stopping points of 2 seconds and 4 seconds. And then, of course, you're going to need to go get your r prime because that's going to give you your dx dy. The derivative of t is just 1. The derivative of 2t minus 3 is just 2. And I'm kind of running out of room. But the line integral xy dx plus x squared dy becomes the integral going from 2 to 4 seconds because we said so. And then you replace your x with t, your y with 2t minus 3, your dx is 1 dt plus x squared, that's going to be t squared, and then your dy is 2 dt. And I'm just going to tell you that, do all the anti-differentiation and so on, and you'll get 170 thirds. Now, so far, what's the point? The first answer we got was 70, and this answer is totally different. It's 170 thirds. So, well, so what? So, you know, we were doing a line integral over different curves. Yeah, I know that, but things will be, just keep your eye on the ball here. So I'm going to do the last one real fast. So this last part C here, they're saying, okay, do the same line integral all over again, but they parameterized. So you're given the parameterization. Oh, that's very nice of them. Finally, we don't have to do so much hard work. Woo! It's like, hey, thanks, guys. So they gave you x and y, and they gave you a time interval going from 1 second to 5 thirds. You do have to get the dx and the dy, though. So for letter C here, dx is 3, and dy is the derivative of 3t squared minus 2t, like that. And so then this line integral xy dx plus x squared dy is going to become a regular integral going from 1 to 5 thirds. And your x is 3t minus 1, your y is 3t squared minus 2t, your dx is 3 dt plus x squared, that's going to be 3t minus 1 squared, times your dy, but that's 6t minus 2 dy. And, you know, this is going to be a little bit of a pain to integrate, blah, 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 etc. And you get 58. Okay, so what's the point? We got 3 different answers for this line integral along 3 different paths. What did the paths share in common, though? They did have a common denominator. So I want you to notice, even though all answers were different, all 3 of these curves had the same starting and stopping point. And if you don't believe me, this curve here, the 3t minus 1, 3t squared minus 2t, if you did graph it, it would be the portion of a parabola with the starting point at 2, 1 and the ending point at 4, 5. So all 3 of these line integrals share something in common, not much, but the same starting and stopping point is the big deal. So now let's do another page of line integrals. So I'm just giving you lots of examples so that you can really excel at this, okay? So there's this physics fact that if you're in a gravitational field and you're computing the work done on some object by the gravity as it moves between 2 points, it turns out it's independent of the path taken by the object. So, you know, in other words, here's point A and here's point B. Let's say you've got some gravity, you know, working on you, pulling you down. And let's say, you know, you decided to go from point A to point B like this. Woo! You would get some amount of work done. And let's say you decided on another day, you know, this could be your, you know, going from your home to work. So here's your home. Let's say you want a straight shot. It looks like, oh, you should be, you know, the work done should be less, right? Because it's a shorter path. No, it turns out the work done on you by gravity is the same as if you had taken the long path. Okay. And that's really weird. It's like, well, how is that possible to have the work done be exactly the same, even if the path is totally different? You'll see in a moment. So let's say you're given a new vector field. There it is. It's given to you in a different format, not component form, but this linear combination of the standard unit vector format. And let's say they give you the starting and stopping points along 3 different ways. So 0, 0, 0, 0 to the point 1, 1 in 3 different ways. So the first curve, this guy here, is just a straight shot, y equals x. Okay? The second curve shares the starting and stopping point, but it's going to go along a sideways parabola like this, x equals y squared. And then the last curve still shares the same starting and stopping point, but it's going to be along y equals x cubed. Okay, so what about these line integrals? So we're computing work done. By the way, the previous page was also computing work done. They just didn't tell you that. So for letter A, if you do the parameterization, I'll call it R1 of t. Since y is equal to x, let x be t, and y is equal to x. So there you go, t. And then have time go from 0 to 1 seconds. Your R1 prime is going to be 1, 1. So your work is f dotted with dr, which for us is going to be the regular integral going from 0 to 1, and we're going to have to take a dot product here of the vector valued function 1/2 xy, so that's going to be t, comma 1/4 x squared, that'll be t squared, and then the r prime is 1, 1, like so. So this is going to be the dot product of 1/2 t squared, 1/4 t squared, with this constant vector 1, 1. Okay, so do the dot product first before you integrate. And this is easy because 1/2 t squared times 1 is just 1/2 t squared, plus 1/4 t squared times 1 is just 1/4 t squared. Oh, nice. I'm going to combine like terms before I integrate. You don't have to, but it's a little more efficient. And 1/2 plus 1/4 is 3/4. Okay, so we're going to integrate 3/4 t squared, and I get 1/4 t cubed, and evaluate between 0 and 1, and I get 1/4. Final answer, and I'm done with letter A. I'm going fast. If you're lost, watch the video recording. Letter B, you're going to go along x equals y squared. Now here, folks, this is a function of y, not a function of x. So when you're parameterizing a function of y, you let y be t instead of x be t. And x is equal to y squared, and your time will still go from 0, 0 to 1, 1, so it'll be a match. Go get your velocity vector, because you always need to do that anytime you do a line integral. And then the work done is going to be this f dot dr line integral. So the work done will be a regular integral going from 0 to 1, and you're going to have to take a dot product. You're going to have the velocity vector be one of the vectors that's involved in the dot product. And then you have to rewrite your force field in terms of t's. So x gets replaced with x squared, and y gets replaced with t, because you're just stealing the components from your vector valued function. So you're going to have 1/2, and then x is t squared t. And then the second component for this vector field is 1/4 x squared, but that's t squared squared. Yeah. So this first component is 1/2 t cubed, and this second component is 1/4 t to the 4th. So when we do the dot product, we're going to have 1/2 t cubed multiply with 2t, the first component from the velocity vector, plus 1/4 t to the 4th times 1. Oh, okay. But this first term is really, after we do some canceling here, this is just t to the 4th, and you're adding that to another t to the 4th term, so why not combine? They're like terms. And I am going to combine. I get 5/4 t to the 4th, and when I integrate, I get 1/4 t to the 5th, going from 0 to 1. I still get 1/4 as the answer. Oh my goodness, I got the same answer. Look at this. The previous answer was a 4th, and this new answer is a 4th. Was that just a fluke? It turns out it's not. You'll see in a moment. Let's do the last one. Of course, I never give myself enough room. So let's add a page and do the third problem here. So letter C, you've got y equals x cubed. So when I parameterize, I get r, I'll call this r3 of t. This is a function of x, so just let x be t, and then y is just t cubed. And we got to get t will also go from 0 to 1. That'll work. R3 prime, the derivative of t is 1. Derivative of tq is 3t squared. Okay, so work, which is f dot dr, is going to be the regular integral going from 0 to 1. And we're going to take a dot product of the vector field with our prime. And so the we have a half xy here, which is going to become a half t cubed. And then the other component is a quarter x squared. So that'll be a quarter t squared. Okay, so this is really 1/2 t to the 4th. So now when we do our dot product, we'll have a half t to the 4th times 1 plus a quarter t squared times the 3t squared. There's the dot product like that. And it turns out these are like terms because these are both t to the 4th terms. So how about if I combine like terms before I integrate? You don't have to, but it sure is a little easier to read. So you're really integrating. Oh, once again, we did this already. Yeah, and we did this already. So we also get a 4th. Okay, so what is the big deal here? After all of this, am I getting somewhere? Yes, I'm trying to make a point. All 3 answers are the same. That's the answer to this question. What do I notice about all 3 answers? They're the same. Okay, well, you know, with the other page, we didn't have them the same. Yeah, I know. And what did both pages have in common? Both pages, all the paths had the same starting and stopping points. So notice that as your common denominator. But this vector field that we were working with, the question here is it conservative? Yes or no? Well, remember the test for a conservative vector field, which I did already, is does dn dx equal dm dy? I did that in a previous lecture. So let's check it for this vector field. Well, dn dx, the partial of 1/4 x squared with respect to x is what? It's dn dx is 1/4 times 2x, which is what, x over 2? Yeah. And how about dm dy? The partial of 1/2 xy with respect to y. I get a half x. Do you notice that these are equal? Please say yes.
Yes.
Yes. So is the vector field conservative?
Yes.
Yes. It sure as heck is. So then what? Let's go get mama. Remember? If you have a conservative vector field, you can get mama, which is the potential function. So let's go do that now. So let's go get the potential function for the vector field f xy, which has these components, a half xy and 1/4 x squared. This is the m, this is the n. So I taught you how to recover the potential function in a previous lecture, and I also warned you that if you don't do it my way, I'm going to take away a lot of points. I'm going to repeat that again, the risk of being redundant. If you do it the way the show an example button does when you're doing your online homework, I don't care even if you get the right answer. I'm not giving it to you. I'm going to be kind of strict here. So I know some of you fall asleep during lecture. You're like, yeah, whatever. I'll learn it during the homework. And then you do learn it during the homework. And you're doing all sorts of weird and wacky stuff that I didn't even do. So to recover mama, you're going to integrate with respect to x, the m component. You're going to integrate with respect to y, the n component. You'll add the results. And if there are any duplicates, you don't add the duplicates together. You take one instance of any duplicate. All right. So you're going to integrate a half xy with respect to x. So that means you're going to hold y constant. You treat y as a constant multiple. And it turns out that the antiderivative here, you know, you pull out the y, the antiderivative of x with respect to x is x squared over 2. And so plus extra junk. So let's just clean this up. This looks like x squared y over 4 plus don't just put plus C. I will dock you points. I want to see you acknowledge the fact that it could be just a pure constant, and it could have, because you didn't recover with respect to y, you were recovering with respect to x only, you're going to have some function of y, say g of y. I'm going to tell you right now, you neglect to put that in there, I will dock you a point every time you screw up. So n dy is the integral of a quarter x squared with respect to y, but you're holding x constant, so that's just going to be a 1/4 x squared y, and then you need to acknowledge that you were recovering with respect to y, so this extra junk is going to be a constant plus f of x. And then you add the results. But wait a minute, aren't these guys duplicates? Yes?
Yes.
Do not
Yes.
add them together. You're just going to take one instance. So your recovered potential function is one of those guys plus C. And there's mama right there. And notice this is what we call a scalar function. This is a scalar function, not because it's like a scalar, like a pure number, like the number 5 or something, but it's not a vector field. It's not a vector function. It's a scalar function. Okay, so I'm going to save this for later and come back to it in a moment after I complete the fundamental theorem of line integrals. So let's go now and do the fundamental theorem of line integrals. This is the big deal about this section. There's two big deals, but this is the first biggie. The first biggie is, what the heck is the fundamental theorem of line integrals? So I'm not even sure I should teach it to you guys. Do you deserve it?
Yes.
Really?
Yeah.
Well, if you think you deserve it, answer this question first, and then maybe I'll repay you with telling you what the fundamental theorem of line integrals is. Here's a quick question for you. Do you know what the fundamental theorem of calculus says? Because if you do, then you're worthy. Oops, fundamental theorem of calculus says. Feel like Ferris Bueller's Day Off, you know, Ben Stein that plays the professor. Anybody? Anybody?
Isn't it
Bueller? Bueller? Anybody?
isn't it the integral from like a to b of f of x? Is that what it is?
That's how it starts. Good job. Then what? Keep going.
Is it the thing where it's equal to the limit? That's like a summation with a limit, or is it not that?
No, it's not that. Look, if you don't know the fundamental theorem of calculus, why am I even bothering? What the heck am I doing here? You guys are graduates of Calc 1 and Calc 2. Right? That's how you got here. So you should know the fundamental theorem of calculus. You actually use it all the darn time.
Wait, did you just want us to write like how it works out, or like what it
Well,
is
what does
used
it
for?
say? What does it say? You should go look in your calculus book right now.
Well,
I
isn't
mean,
it
you
just
can't work this out because you don't know what f of x is, right? But the theorem tells you something, and that's sort of my point. And I'm not going to belabor it because we're short on time, so I'm just going to tell you. But I just want to say that when I write this down, if I put something about the fundamental theorem of calculus on a future exam or quiz, would you be able to answer it? I hope so.
Probably would. I just don't remember like what it is off the top of my head.
So here's what it says. Now, when I tell you this, you're going to just kick yourself, okay? You first have to get an antiderivative. We'll call it big F. And then you evaluate it between the limits A and B. And the fundamental theorem of calculus tells you also that you first evaluate it at the upper limit
Minus
and then minus the lower limit. And we're done. Now, that's part one of the fundamental theorem of calculus. There's actually a lesser known part 2, that's just as good really as part 1. So in case you don't remember it, I'll sort of give you sort of the cheesy, sleazy version of it. But do you remember that if you're integrating, say, a derivative of a function, like, well, maybe I'll do like a to x. Does anybody remember how to do this part 2? I'll give you a hint. Integration and differentiation are inverse operations of each other.
Won't you just be ft?
So you're going to, this is like df dt here, right? Yeah, so you're going to go, all right, well, when you integrate a derivative, don't you just get back the original function? Hello?
Yes.
Okay, so this is the part 2 right here. All right, so I'm just letting you know that this stuff right here, this is basic stuff that Calculus 1 student learns, and then the rest of the calculus you use it. So how is that helpful to us? Like, well, okay, we knew that. All right, well, did you? I had to ask, and then everybody's like, oh, I don't know. All right. So go get this tattooed on your leg or your arm. And I'm not joking. Like, I have a meme where I have somebody a picture of a tattoo. Okay. So now let's do the fundamental theorem of line integrals. I'm going to prove it, and then I'm going to do some examples using it. Okay. So here is the fundamental theorem of line integrals. If you've got a piecewise smooth curve and it's lying on some open region R, and somebody already parameterizes it for you, hey, thanks, appreciate it. And so you also know the time interval, and you've got a vector field that's conservative. It has to be conservative, otherwise the fundamental theorem of line integrals cannot be applied. So this is key. And that could be a good true-false question right there. Does the vector field have to be conservative for the fundamental theorem of line integrals to apply? True. Okay, and you want M and N to be continuous in the region, and then you're fine. And so here is what this fundamental theorem says. And this is cool beans, people. I mean, I love this theorem. If you're doing a line integral, any line integral, okay, that a vector field one, and your vector field is conservative. So what does that mean? It means that there's a mama out there. He's the gradient of mama. So you can rewrite your vector field as using gradient notation, gradient of f, where f is, I'm going to put where f is the potential function for the vector field f, dotted with dr, going from A to B. Then this is, since the gradient, remember the gradient is a vector that's got partials for its derivative, and you're integrating partials. So basically what you're going to get back is the function itself. So you're going to get like x of t, y of t here, going between A and B. And so your answer is going to be f evaluated at x of b, y of b, minus f evaluated at x of a, y of a. Now, I know some of you are very non-impressed right now. You're like, who cares? This looks really hard. Here's the good news. You don't have to parameterize at all. If you are given a line integral with the curve, and all you need is the starting and stopping point, because this right here is actually the ending point of your curve. You just plug that into mama. And this x of a, y of b is actually the coordinates of the starting point of the curve. And you plug that into your mama. And then you're going to get your answer. Okay? I'm going to do a proof of the theorem here real quick because it's kind of fun for me. I got to have some fun in this class. Assume that C is a smooth curve. And smooth means there's no sharp corners or cusps. And so your vector valued function doesn't have a derivative who's 0 or undefined. And because your vector field F is a conservative vector field. You're given that. Otherwise, you can't even use this theorem. Like, don't even think about it. Because that means it has a potential function. That's that scalar function we talked about, f, x, y. And the vector field, fxy, is the gradient of the potential function, which means it has a special look to it. It's a vector that's got the partial derivatives as components. Okay, so then it follows that this line integral, if you're trying to do one of these funky line integrals like f dot dr, like so, is going to look like, you know, the integral going from a to b. You've got your partials in there, and you're going to dot product that with the vector valued function's derivative, also known as the velocity vector. Okay, so then when I actually perform the dot product here, okay, I'll take fx, multiply it with dx dt, plus the other partial, multiply him with dy dt, and then dt. All right, now what? Well, what do we have here? What I want you to get here is, what does this look like to you? So you may be going, well, I don't know, I don't care. But I claim that this has a chain rule look to it. Do you guys remember the chain rule from a couple of chapters ago?
Yes.
So like, what do I mean? Well, if you have a function here, f of xy, and you've got, you know, your x and you've got your y, and both x and y are functions of t, if I asked you for df dt, you know, you'd go down this branch, you get fx, and then you multiply by dx dt, plus, and then you'd go down this other branch, fy, and then down this branch, dy dt, right? Is this looking familiar to anybody?
Yes.
Okay, so what I'm going to do is I'm going to apply the chain rule backwards. So I'm going to use the chain rule backwards on this sum. I'm just going to replace it with what it is. It's just the derivative of f, that scalar function, with respect to t, with respect to time t. And then using our knowledge from the fundamental theorem of calculus, part 2, fundamental theorem of calc, part 2, which says that when you integrate a derivative, since those are inverse operations, what do you get? You get the function, and then you have your x of t, y of t here, and then you evaluate between time going from a to b seconds, and so you're going to get x of b, y of b, and that's your ending point, minus f evaluated at x of a, y of a, and that's your function evaluated at your beginning point. And that's the end of the proof, which is pretty cool. So what I love about that proof is it involves the chain rule, which is a very powerful theorem, one of the biggest powerful theorems you've learned this whole semester, as well as a huge powerful theorem, fundamental theorem of calculus, that you learned in Calc 1, and you use it all the time. Okay, now what about 3D? What if you had to do this in 3D? Well, I haven't told you how to figure out and recover a potential function for a conservative 3D vector, and I will soon, but let me just say that if we did extend the fundamental theorem of line integrals to a 3D conservative vector field, it works just as well. But I'm kind of waiting to tell you how to do that. So be patient. I know I'm just trying to get to it. I don't even know where I am now. Anytime I use my erase tool, it takes me, who knows where it takes me. Okay, so here we're going to extend the theorem for 3D. After you recover the mama for 3D, which I haven't showed you how to do yet, you do get the gradient of your potential function. And then you would just simply apply the fundamental theorem, and you would evaluate at the ending point minus f evaluated at the starting point of your curve. No parameterization needed. This is the benefit to you. So for those of you who like, you've been kind of like snoring when I parameterize curves, you're like, oh man, I hate this parameterization. The good news for you is if somebody gives you a scalar, or not a scalar line integral, a vector line integral, and you can prove the vector field's conservative, you don't give a darn about the curve other than the starting and stopping points. That's it. Like, don't bother parameterizing it. Don't waste time. And if you do waste time, I will take away points. Because why waste time? I mean, do you like wasting time? I don't like it. So I don't even want to see it on your paper. Now, we're going to do the previous example all over again. What? Oh, man, what do you mean? So what do I mean by example 2 all over again, which took us like forever? We did example 2 3 separate times. Let me remind you here, for 3 different paths. But the common denominator with all those paths was they each had the same beginning point, 0, 0, and the same ending point, 1, 1. And we had to parameterize, 3 times. We got 1/4 every time, though. So that was the common thing, is they got the same answer. Is there a quicker and dirtier way we could have done any of those problems? Yeah, we could have avoided parameterizing altogether. And if they said, hey, go do this line integral, and here's the vector field, and the only information you have is the starting point and the ending point, I'm like, sweet. And so we already got the potential function. Remember, the potential function was what? Anybody remember it? Remember I said save it for later? Right here.
That.
And the plus C is going to not be needed because it'll subtract out. So you only need to put any non-constant terms in here. So you're going to have 1/4 x squared y, and you're going to evaluate it between the limits. But the limits now, you don't even have to figure out the starting and stopping time. You don't care what time is doing. You just want the coordinates of the starting and ending point only. You just need the coordinates. And the fundamental theorem of calculus does say evaluate at the upper limit first and minus the lower limit, which is going to be a big fat 0 here. And we get our final answer, which is 1/4. And right now, if you're not saying, like, have your eyes wide open going, wow, you are not paying attention, because that's a big wow. Don't you agree that was a lot less work to do?
It was a lot of work that was just like saved a lot of time.
You save so much time. It's like, wow, I love this fundamental theorem of line integrals. Well, where can I get some more of that? That's what you should be saying. How come you didn't teach us this before? Well, you weren't ready. Now, don't get too excited, because look, if your vector field is not conservative, you're still going to have to do it by brute force. You will have to parameterize and do all the hard work that we did. But if your vector field is conservative, just go get mama and evaluate mama between the beginning and ending points. And you don't have any other work to do. It's lovely. Okay, there you go. So let's look at another example, example 3. We're going to evaluate this line integral, FDR, with this force field, fxy, 2xy, x squared minus y. And now the curve, they're not even giving us any information about the curve. And so we couldn't even do this if this weren't conservative, because they're not even giving us if it's a straight curve or whatever. They're telling us it is a smooth curve, which is helpful. And this is not necessarily a line. So don't get, I get people who go, that I'm going to parameterize it, and it's a straight line. Well, you have to be careful, because they didn't even say that anywhere. And does it matter for us? No, we don't care. Because we have access to the fundamental theorem of line integrals, I'm going to prove it first. So first, we're going to prove that F is a conservative vector field. Because I can't tell by looking at it, and you certainly can't either. So how do I prove it? You prove it by showing that dn dx is indeed equal to dm dy. That will prove to me it's a conservative vector field. Okay, so the first component is understood to be m, as in Mary, and the second component is your n, as in Nancy. So what is dn dy? Well, the derivative of, dn dx, what is the derivative of x squared minus y with respect to x? Hello.
2x.
2x. And what is the partial of m with respect to y?
2x.
It's also 2x. And these are equal. So good news. It's conservative. So what does that mean? Go get mama. Go get the potential function. So we need to recover f of xy, which is the potential function. I call that mama. I'll tell you a quick funny story. I have a student who's now a full-blown engineer, and he's working for, I think they call it NavWar now. Used to be called SPAWAR, and it used to be General Dynamics. I used to work there many years ago. And so he took me for like Calc 2, Calc 3, differential equations, and so on. And he was a good student. He went to UC Berkeley and got a degree in nuclear engineering, I think. Yeah. I think he took me for, no, he didn't take me for programming. I wanted him to, though. So he was doing some upper division work at Cal Berkeley, and he noticed that he knew how to do a whole bunch of problems, and he and his classmates didn't. They were all lost. And he had taken me for Calc 3, and he goes, all we were doing was working with vector fields that you had to go get mama. And I would just tell my buddies, hey, go get mama. And they were like, what? And it cracked me up because he goes, yeah, just go get the potential function. And so he had to like teach them, you know, how to do the stuff. So there you go. All this work that I'm doing for you in the future, you'll hopefully be tutoring your classmates because you know what you're doing. And for some reason, they didn't get it. So here we go. So you're going to recover the potential function. So you're going to integrate m with respect to x. So what is the integral of 2xy with respect to x? I think it's x squared y. And then you're going to acknowledge the extra junk, g of y. And then you're going to go integrate again, but you're going to integrate the n component, x squared minus y, with respect to y. So the first term, x squared with respect to y, is x squared y, and then minus y squared over 2, plus extra junk. So how about h of x? Because you were integrating with respect to y, so you have to acknowledge there is other junk with respect to x, so hence h of x. And then, hey, do you notice you have duplicates? I got duplicates there. Should I add the duplicates together? Yes or no?
No.
Oh,
No, don't do that. Otherwise, I'll take away your points. Just take one. So your mama function, fxy, you'll take one instance of the duplicates, and you also have a minus y squared over 2. And of course, we'll say plus c, but the plus c doesn't come into effect when you're actually doing your fundamental theorem. And so now you're ready to apply your fundamental theorem. So what am I saying? So this line integral they're asking us to do with the curve, you don't have to do it. You're just going to go, all right, I have the potential function x squared y minus y squared over 2, and I'm going to evaluate that between the starting point and the ending point. That's it. And so you always want to plug in the ending point first. That's the fundamental theorem of calculus. Minus, and then you evaluate at the lower limit, which is the beginning point. Yes, it matters the order. Don't blow this and do it backwards. I will take off a lot of points because that's no good. What do I get here? La, la, la. Okay, and I get 2 minus 2 minus 4 plus 8, and add it all together, and I get 4. Fine. So what was the beauty of that? The beauty of that problem was it was a conservative vector field. I did not have to parameterize. All I had to do was go recover the potential function and evaluate the potential function between the beginning and ending points. And that is the fundamental theorem of line integrals. And it's a wonderful thing. Okay. So I do want to talk about independence of path now. So the last piece of this section is going to tie some other things together with the fundamental theorem. and conservative vector fields. So let's go and do the little wrap up here. So what of it? So what of independence of path? So from the fundamental theorem of line integrals, what did we get? If f is continuous conservative in an open region R, then the value of this line integral is going to be the same for every piecewise smooth curve from one fixed point to another fixed point. It won't matter the path. So we say that the value of the line integral is independent of path, because the only thing it cares about is the beginning and ending points of the path. We don't care if the path is curvy or, you know, a straight line, or if it goes around and takes 200 miles to get between point A and point B, as long as it's got those beginning and ending parts of the journey there. Okay, now let's do a quick definition here, and then we'll use that for the next theorem. So you need to know what a connected region is. So here's a picture right here that tells you what it is. So a connected region looks like that. So what does it mean? If you've got point A and point B here, you know, point A, point B, you can get to point A and B and you can stay in the region. This is not a connected region. I like to think of this as Hawaii. You know, you've got different islands. It's not connected. Hawaii is not connected. Like if you've got like the big island here and then another island like Maui, and you want to get from the big island to Maui, well, you're going to have to actually go off the island into the Pacific Ocean there in order to get from point A to point B. So it's not connected. So here's the official definition here. We say it's connected if any two points in the region can be joined by a piecewise smooth curve lying entirely within the region. Otherwise, it's not connected. And we need connectedness for this next theorem. So the independence of path and conservative vector field says if f, that's your vector field, is continuous on an open connected region, in other words, not Hawaii, then the line integral, which looks like this, f dot dr, is independent of path if and only if, and I'm going to abbreviate if and only if with IFF, and so you may see this in another class sometime in your future. IFF is abbreviation for if and only if f, that's the vector field, is conservative. Now, the importance for you to know about an IFF statement is it's what we call a double header statement. You can read it in both directions. And so you can also, using symbols, identify an IFF statement with a double header arrow. And I can read it forwards and backwards, and it's still true. Now, not all statements are like this. If you have a regular if statement, it can only be read in the forwards direction and still be valid. But an IFF double header, you can read it forwards and backwards, and it's still true. So if I read it backwards, I'll start over here. If f is conservative, then the line integral is independent of path. It's still true. And I can read it in the forwards direction. The line integral is independent of path if the vector field is conservative. So both directions, it's still true. So that's the theorem for independence of path. So what's that got to do with us? Well, on the next couple problems here, if they ask you to prove that a line integral is independent of path, how would you do that? How would you prove that a line integral is independent of path? In other words, it doesn't care about anything except for the starting and stopping points. What would be the quickie proof?
You would show that it's conservative.
Bingo.
Statement.
Thank you, Lizette. Exactly right. All you need to do for the proof, and you'll be done, is show that f is a conservative vector field. And that would be enough. That's plenty proof. And then they want us to evaluate this line integral. Now here's some weird notation. Notice that on this line integral, they put the coordinates of the starting and stopping points on the symbol itself. Is that legal? Yes, you will see that in lots and lots of calculus textbooks. So this is your first introduction to the notation where you have a line integral where somebody actually puts the little itty bitty points, starting and stopping points on the integral symbol itself. Pretty cute, huh? I love it. I love it. So let's prove that this is a conservative vector field. The first component we call M. The second component we call N. Let's show that dn dx is in fact the same as dm dy. Here we go. dn dx. The derivative of 3xy squared with respect to x. I get 3y squared. dm dy, the partial of m with respect to y. So when we take the derivative of 2x plus y cubed with respect to y, I get 3y squared, don't you? Hey, these are equal. What does that mean? Haha, conservative vector field. Go get mama. So by the way, you're done showing it's independent of path. So you can right away, you can say, therefore, the line integral is independent of path. I just proved it. That's enough. You don't have to do anything more. You don't have to evaluate it. Nothing. You just proved you have independence of path by the theorem. Now, they did want us to evaluate that cute line integral. So if we're going to evaluate it, we're going to use the fundamental theorem of line integrals. We love the fundamental theorem of line integrals because it's going to help us integrate that line integral. So first, go get mama. Yep, go get mama. So you're going to integrate the first component of your vector field, 2x plus y cubed, with respect to x. So you're going to get, what, x squared plus xy cubed plus g of y. Then you're going to integrate the other component, 3xy squared plus 4, but with respect to y. I get xy cubed plus 4y plus, acknowledge you didn't integrate with respect to x this time, so h of x. Now, I hope everybody in the room sees that I have some duplicates here showing up in both of the integrals. Please do not add them together. Your potential function is, I'll take one instance of the duplicates, and then I do have a couple other terms there. I got the x squared, got to have that guy in there, plus the 4y, plus some constant. And now this line integral that they want us to do with a beginning point of 0, 1 and an ending point of 2, 3 is going to be the potential function xy cubed plus x squared plus 4y evaluated between the beginning and ending points. That's it. And we plug in the ending point first. Please don't do this wrong. You don't want to do it backwards. Minus, and then I'll plug in the beginning point with x coordinate of 0. So those first two terms go to 0. Okay, fine. And then add all this junk together and whatever. I get 66. So that is the line integral's value. Now, what if somebody said prove a line integral is not independent of path? How do you think you would do that? How would you prove a line integral is not independent of path?
Show dn dx does not equal dn dy.
Very good. You're going to show that f is not conservative. In other words, you're going to show that dn dx doesn't give you the same result as dm dy. And that's proof enough. You just proved it. So let's go do it. So where's the m and where's the n though on this one? This is differential form. And we started off today's lecture with differential form. So you need to just cherry pick your m and your n off of the differential form. So whatever's multiplying with the dx is your m. It's understood. And then you have a plus, and be careful, this has to be a plus. If they try to trick you with a minus, and I will, change it to plus a negative so that the negative will be part of your n, because otherwise you're going to blow it. And they try to trick you in differential equations also when you're given exact equations. So if you learn it here first, then you won't screw up there. So what is dn dx? The partial of 3x y squared with respect to x. I get 3y squared. What about dm dy? The partial of x squared y with respect to y. I get x squared. You see how these are not the same? Not equal. And that means not conservative. So you wouldn't be allowed to go get a potential function because one doesn't even exist. Now, do we even have enough information to do this line integral? And the answer is no, we don't even have enough information. Why not? Because even though they gave us the starting and stopping points, this is dependent on the path. This is path dependent, and they didn't tell us the path from the starting and stopping points. They didn't tell us if it were a straight line or something curvy or whatever, because if we did have to evaluate it, we'd have to use brute force. We'd have to parameterize in the whole 9 yards, and it will be a little painful. So we can't even do this one because they didn't give us any additional information about the path, which it is dependent on. And I'm done with today's lecture. I'll wrap the rest of this up next time. You won't need the remaining stuff for taking the quiz this weekend. You're good to go. And I hope you have a good weekend. I do have office hours today between noon and 2. You're always welcome to come anytime. Okay, bye.
Have a good day.
You too.
See you, Ms. Husky.
See ya.